Welcome back to time series analysis for 2017. I promised some of you this afternoon that I will give a small presentation of some code, how to do things. So I will use that to first give some examples, and then I will go through a sample solution of the coding exercise that I gave you earlier today. So let's just get into our studio and see how we get things done. Now, I don't always do this, but sometimes it's nice to just clear everything that is in your environment. And if you're going to read data from files, basically two ways: either set the directory, or whenever you're going to read data in, you can specify the full path here. I just have preference for working in the particular directory that I'm in. What we asked to do is to have given some data, we should just predict 50 time steps ahead. So let's just read the data. We use the header argument here to say the first line includes the data. We should also show what is in there. So this data frame here contains 3 columns. First some X, and then some time units that just integers, and then something that we're not going to use for today. So it's always a good thing to start plotting the data. I'll set some parameters. I want one plot, and I want to adjust the margins. I'll just make the plot. So the latter margin out here is how many lines of text height is first argument 3 here, 3 there, 2 there, and 1 at the last side. So that's what mar is given, and then MGP is how many lines out are you placing the axis labels and the numbering. And this is just my preferred settings. So now they're shared, you can do whatever. Plotting, well, labels and whatever, that all works just fine. Let's just start out looking at data and say, well, could it be just a linear model? Let's give it a shot. For now, I'll just use the default LM function. The disadvantage of doing this in a demo is that to show what is actually out there, I have to kind of do that. But another way of doing it is to add parentheses around the call, because then it will also evaluate it and show me the estimate that's out there. Now, what I've said repeatedly is, well, we like to have estimates, but we also like measures of uncertainty. So I do the summary.lm and look at well, these are very significant. We have standard error of estimates. Let's just show the fitted line. At first it looks fine. So let's just look at, in this object that we saved, analysis.x. When you print it, it just gives you this. But if you look at the names of that, we can see that it has a lot of other things in here. Among other things, we have all the residuals here, and we also have, you say, how many observations do we have, and we have degrees of freedom for the residuals. But right now, we'll just compare the summary with our own estimate of sigma hat. It's the sum of the squared residuals. Sum of the squared residuals divided by the number of observations minus the number of parameters, and we take the square root of that to get a standard error, and we see that indeed the LM function gives you 1.062, and we get the same thing within rounding. So we can also try to do it all manually using the design matrix. In this case, we just have a column of ones and then the time here. So it looks like this. And to find theta manually, what we have to do is to solve the normal equation, x transpose x, solve that, equal to, multiply by theta equal to x transpose y, do that here. And if we look at the coefficients from the linear model, we see that we get the exact same numbers. As expected. Now we were asked originally to predict 50 steps ahead. First we'll do it in the tedious manual way, creating a vector of 50 zeros as a space holder, and then we'll do them one at a time and say what is actually the uncertainty that we're looking at here. We have for the t-distribution we have 498 degrees of freedom, and we want to do a 95% interval, so we look at the 97.5% quantile, have an estimate of sigma hat or sigma, and then we have the usual, when doing the prediction error in a general linear model, we have to multiply this with 1 plus the predictor times the inverse of x transpose x, and then the predictor again with the appropriate transposes. So that's it. If I do that all in one go, now I get how much to add to the expected value to get to the uncertain, to get to the prediction intervals. Predictions, well, I can do it creating a data frame with x hat being the predictions. It's the coefficients, the first coefficient with the intercept plus the second coefficient times the time point where we want to get predictions out here. Let's just run that. Now those are the predictions, and then we can get to the lower boundary by subtracting the prediction interval and the upper boundary by adding that. So now we have a structure where the first 6 lines are like this, and then of course continue all the way down. So now let's just redo the plot. First make space at the right hand side to the 50 predictions. Let's first plot the line of the fitted values, and then we can plot the first column here, x hat, here with all the predictions, and then we want to add the lower and upper. Let's do them one by one, like this. So when we look at this, that is basically doing the prediction and giving us a 95% prediction interval. And it looks pretty much fine, but that was a lot of line of code for doing something that could be done very, very easily. So rather than doing all this from line 42 down to 65, what we'll do instead is first we make a data frame with the prediction time point we want, then we run the prediction function here, and we say we want a prediction interval. The default is 95%, and we want to use the data we just created as our new data, and we use this linear model object to do the predictions. If we look at the head of that, well, we actually already now we have the fit and the lower and upper bounds. So now we just have to plot it. First, again, we'll plot the points, same as before, and then I will add the fitted line values just as before. But now I will use matte lines because here I have 3 columns for the predictions. I will plot the time point for the predictions, and then I'll plot the 3 columns. I will have them all with same width and same color. 2 is red. And then the line type, I will have a full drawn line for the expected value and dashed lines for the prediction interval. And if we want to, we can do confidence intervals as well. Just 2 lines, boom, we got that. So now the question is, are we done? Well, we did do the prediction 50 steps ahead. But if we actually use the best model, what should we do? Well, we should look at do some validation, look at the residuals. So let's just make a plot at first of the residuals. They're supposed to be just homogeneous, look nice. It's not too bad. It's a nice spread. Just compare where they have mean value 0. Doesn't really change the picture much. Now the distribution, we can do that in many ways. One way is to look at a histogram of all the residuals and then showing a curve representing the density of the normal distribution with the same mean value and standard deviation. It looks nice. On the other hand, a histogram is not the most effective things. You could also do a non-parametric test called the Kolmogorov-Smirnov test, for instance, comparing with the normal distribution. We get a p-value that is way higher than 0.05, so there's no significant departure from normality. Rather than looking at a histogram, I tend to prefer to look at the empirical cumulative distribution function like here. And then again, I can add what is the expected curve here. Then it's easier to see if probability mass is moved somewhere else. And this is actually what happens inside the Kolmogorov-Smirnov test. Then you're looking at the largest vertical difference between those two. So these are all, and we can continue looking at ways to assess normality. A QQ plot is a classical thing. I guess you've seen this before. I just want to add the QQ line just to say what are we comparing with, and nothing really sticks out because this is way too little. And that is the default. We can also, rather than the red line, draw our own line where the slope is the estimated sigma. And they are almost identical, but not quite. If we look at it a little bit closer, what we can see is that the slopes are different. So the blue line here, based on sigma, takes all points into account, whereas the red line goes through two quantiles. And then it's just a line through those points. So the default is always a nice fit in the center part. And either line, your focus should be on how are things along those lines. Here, everything is fine. Okay, next, let's look at the residuals and the fitted values. So we have the residuals up here and have the fitted values down here. There's no really pattern. We can also look at the residuals versus time. And again, it looks, in its case, actually much like the other one. It's not always the case. Again, it depends on which kind of model, which kind of data, and so forth. Now, so far you can say everything is fine. But if you look at it, it may seem there's a small tendency that when time is low, the residuals are more positive. So let's just for once look at the first, not the 500 observations, but let's just look at the first 200. And when you just look at the scatter plot like this of the residuals, of the data, sorry, it looks okay. But now let's just add our fitted values. So it looks like there's no slope, but the estimate that we got is a quite significant slope. And we're looking at the 200 out of the 500 observations. So let's just look at the data again. Notice a different way of doing plotting with a functional argument. Now, we could try to say, well, actually it looks like there is a change in slope. So up here the slope is larger and then it's smaller down here. So we could try to do a second order model as a second order polynomial instead of just a first order polynomial. So we'll try to do use time squared as well. Look at this. You could do it like this. Another way of doing it is to update the existing model by adding the time square element. But again, what we want to look at is to look at the significance of the parameters to start validating the model. First thing to notice is that only the second order term is significant. And we want to remove the least significant term first and then see what happens. And as long as we have continuous variables and offset 0 is meaningful, then we can remove either of these. So we take the one with the highest p-value and start by removing the intercept. Again, we update the model and we look at a summary of this updated model. Yet again, the slope is still not significant, so we'll update the model again. And now we only have the second order term left, and it's highly significant. Now you can say, can you actually guess what were the true parameters that were used in this model? I guess this is fairly close to 1.5 times 10 to the minus fifth, and the estimate for sigma is very close to 1, which is actually what was used. And reproducing that, we can get an estimate of sigma hat 2 for this one. Let's just plot, again doing this time a little bit quicker validation. Plotting the residuals, it looks very nice. Histogram, adding the density for the normal distribution. Again, it's hard to tell whether these things are different or not. But I can assure you that this is the right model, so let's just move on instead of doing all the different plots again. Now, let's do the prediction. We want to use the same data frame for prediction here, or same content of it at least, and then we'll just use this model, the largest model for doing the prediction. The rest is the same. Let's plot the data as before. Plot the new fit here with a quadratic model. It looks nice. Let's add the prediction with the quadratic model. Again, it looks nice. And now what I will also do is I want to add the linear model that we did before here, and I'll let you just showing that what the differences are. And we can again zoom in a little bit. And when you look at the data, well, both models are useful, I would say, in the particular case. But I would say the quadratic model is the nicer one in particular case. But the uncertainty here is the width of the interval, the green interval and the red interval. They are quite similar, so there's not much gained, and they're also overlapping quite a bit, the two different models. But of course not identically, because those are prediction intervals where do we expect, given the model, that future observations will be. So that was it for the particular example that I wanted to show you. The next step is to go to the case that I want you to work on for today. So I will just swap to another file here. And what I asked you to do was first to simulate some data and plot it. Looks something like this. Of course, there's a randomizer in there, so you won't have the exact same, but same. Second question was specify a suitable global trend model for the data. Well, we can see that we simulated a quadratic model, and then we should also probably consider a quadratic trend model. So the f function is a column vector with a 1, a j, and a j squared half. And the L, we'll define that as a function. We will define the L operator as the following. Have a look in the book. And we will pre-calculate the inverse because we will need it many times just to see what it looks like. The only difference is you get some minuses in here. Third question is how many observations are needed before an estimate of theta can be obtained? Well, the state here is three-dimensional. So the parameter vector is three-dimensional. So we need 3 observations to get an estimate. However, I would always say that you also need to be able to make an estimate of the uncertainty. So you need at least 1 more, as in 4, to actually get going. Now, you're asked in the fourth question to make recursive estimation of parameters. So basically, and then we should plot the estimated parameters over time, and we should include a measure of uncertainty. Now, we were asked to skip the first 5, that's 4 plus 1, so we will be able to work here. I will share the code with you in Insight, so part of the code here in the beginning is a little bit dense, I should say, content-wise, but first n will say that is the number of observations, and we'll run an init period of 5, and we will then make space, allocate space for f and for h, and then we'll just run through the init period and calculate those. I won't spend time on the particular code in here, but you could spend time looking at what is the structure of it. So I say j takes the value from 0 to init minus 1, that is actually 4 in this case, so init was 5. And I just add the corresponding things here. Now, one thing that I like is always whenever you're going to do something and save and store values, first you allocate space for it. So P is the number of parameters that we want to estimate. I want to store all the theta estimates I get. So I want to have P columns and N rows. I want to estimate sigma at every point in time. And I put NAs in here just to make sure that I don't get any things out where I didn't put anything meaningful in afterwards. Then I want also to have a standard deviation of the thetas. It is essentially a trigonometric covariance matrix, the variance of theta, but right now I'll just look at the diagonal and take the square root of those to get the standard error, just to show that. So first, at time 5 we want to do an estimate, theta hat, and we will store this. Let's just show what it is. So we got indeed 3 parameters in our model. So we start out here, get an estimate of an intercept of -3 as a slope of around 0, and then some curvature. Now we want to make an estimate of sigma. First we'll calculate epsilon by taking the first y values and subtract the predicted values. So here I actually define the design matrix for this here with the corresponding 3 columns. We can just show it, it's not so big here. So this is the design matrix for the first 5, and then we multiply theta on that. And notice we're using the trend model, so we have the current time as our reference point. So let's run the full line. Now we have an estimate of sigma is the sum of the squared epsilons divided by the number of observations that are in here, 5, minus number of parameters, 3. So divided by 2. And then we take the square root of the variance to get to an estimate of sigma. And for theta, we have the same as always. We take the estimate of sigma, and then we take the x transpose x inverse, but that's the inverse of f. And as said, we're just going to focus on the standard deviation, so we'll look at the square root of the diagonal elements. So far so good. That was a long time spent on the first 5. Now we just need to make a loop that covers the rest. So we'll start from the initial part here and go all the way through n. Then we will update f and update h just as we did before. And then we will estimate theta and we will save it. We could do it in one go, but yeah, I just split it for readability. So this is what you have to do the estimates. Now, to add uncertainty, we have different ways of getting an estimate of sigma. So one thing is to do just as we did up there, to create the design matrix and use the estimated theta. This means that as I is going to n, we're just increasing the dimension here. So effectively, the further we go in time, we just keep on increasing the calculation power that is needed here. Now we only have 500 observations, 200 observations, so we're fine here, just doing it. And, oh, sorry, I shouldn't run it. I haven't run anything here yet, so we'll just do it later on in a moment. That's one option. Another option is to say, well, we will just for now store. Oh, sorry, I'll skip the other one. And then we store, based on this sigma all, we will do the same estimate of the standard error of theta. Okay. This in here is just to try to change that sum up there. But then it's not doing exact same thing. We'll discuss it in the next lecture, how to deal with other estimators of sigma. So that's why I commented out. Now let's just run this for loop. Doesn't take long. And let's look at what comes out. I will this time make 3 rows in the plot. First, I'll plot the estimated parameters. Maybe you should just make it a tiny bit larger. Then I will plot the estimated standard deviation of all the parameters. So start out with a large uncertainty and then they just decrease. And finally just plot the sigma that is estimated throughout. It's also stabilizing at some level. And then if we want to do prediction intervals, then we also need to have the associated quantiles from t-distribution from all the different points in time. So we'll just do that once and for all. None of the numbers are produced because I give it a negative degrees of freedom, because it's starting from 1. So I'll put the first init where I didn't do anything to NA to avoid plotting it later on as well. Now let's do some plotting here. So these are theta 1, theta 2, and theta 3. What are the estimates? And we should keep in mind that this is how we see the estimate of the current value that we are at. And we also see here that the uncertainty decreases as time progresses. And if we compare the data later on, you can see that it's actually doing quite well. Second one is the estimate of the slope. It also behaves quite nicely. And last, and third, is the curvature. Now, we are asked to compare in the last question with the performance of a general linear model, just at the end. So I will use the identity operator here to use the time minus n as my time point, because then I have the same reference time, namely time n, when looking at the parameter values. If we do a summary of this model, I get the following. And if I just look at the final estimate of theta, just to compare, the intercept is the same, the slope is the same. However, the estimate for time square is not the same. I don't know if you figured out what the difference is, but I'll scroll back to somewhere where I can show you where the difference is. We go back to the definition of f. We have it here. The third element is j squared half. And that factor of 2 is a difference between the 3.9 per million and per thousand, sorry, and 1.96 per thousand. So there's just a factor of 2 difference here, and that is expected. So that was all I wanted to do for right here, right now. Hope you got a little bit more out of it than just looking at the code, but otherwise we can kind of get back to it and look at it later when we see each other again.